Good evening, everyone. Welcome to IGC classes. So, guys, today we are having our next lecture on physics. So, just I would like to tell you that we are going to start today the magnetism, and along with that, we will discuss the ray optics, and then we will start our previous year questions. So, there are three part we are going to discuss from the three section. Okay. So just I would like to tell that the last three classes we have discussed about the electrostats and about the uh, your Newton law of motions and gravitation, and also we have discussed about the law of motion in the straight line and in the motion in the straight line and motion in the plane, where we discussed about the projectile motion as well. So I hope that you have seen the previous lectures. So just we'll start to quickly share the session with all the friends, so that the maximum students will be able to join the session, and also they will get benefited from this session. And your exam is going to be held on 27th. So this is going to be a very helpful session for all those who are preparing seriously for this exam. Yes, quickly you can join this. So we are going to start with the magnetostats. Yes. So, guys, in the magnetostatic, we have certain topics like your very important topics, such as the Biot-Savart's law and the magnetic field due to the straight conductor, magnetic field due to the circular conductor, and also Ampere's law, current carrying conductor, magnetic dipole moment, and a magnetic material. So, related to these topics, you will be seeing the questions in your Airport Authority of India. So, the topics that we are going to discuss today are in this magnetostatic. First is your Biot-Savart's law, and obviously, for all these topics, we are going to discuss the questions as well. And there are certain previous year questions also. Okay, Ampere's law, the magnetic flux, magnetic dipole moment. Then we will discuss some topic from your next chapter, that is electromagnetic induction. Okay, we will take the question from the electromagnetic induction as well. So those who have prepared the physics part, they will be able to answer the questions of the previous years, and that we will be discussing in the end of the session. Okay, in the end of the session, we will take the previous year questions as well. So here we will also discuss some topic from the Lenge's law, Faraday's law. Okay, mutual induction. All this will be discussed. So what is the Biot-Savart's law? Okay, so what is the Biot-Savart's law? Can you tell me Biot-Savart's law, what it says? Because it is very basic. Yes. So Biot-Savart's law, With the help of experimental results, Bio and Savarts arrive with some mathematical expression that gives us the magnetic field at some point. Okay, if you want to calculate the magnetic field at any point due to the current carrying conductor, then you can calculate by the formula that the dB is directly proportional to I into dl sine theta upon r square. Okay, that is the magnetic flux density due to the current carrying conductor, and that is the small current carrying conductor we are taking. So if we take the proportionality constant, then we have mu naught upon 4 pi dl sine theta divided by r square. So mu naught upon 4 pi is a proportionality constant, and the mu naught is having the value 4 pi into 10 to the power minus 7. Okay, this mu naught is 4 pi into 10 to the power minus 7. So this is our important relation by which we will see the questions in the previous year. So magnetic field lines, how these magnetic field lines looks like. The magnetic field lines emanate from or enter in the surface of a magnetic material at any angle. So if we talk about the uniform and non-uniform, so we have a non-uniform magnetic field looks like non-uniform field. Okay, the non-uniform field will be some like here, then there is a density, more density, then this side, this is the magnitude is not constant. Okay, the magnitude is not constant here, and the direction is not constant means they will be having this type of magnetic field direction. So in this case the direction is not constant, and there may be the magnetic field in this way. Okay, so these are the non-uniform field, and uniform field will be definitely, they will be having the equal distance field lines, and also both the direction and magnitude are constant here. So these are non-magnetic field and this is uniform field. What is the right hand thumb rule? How do you calculate the direction of the magnetic field? So the direction of magnetic field is calculated by the, suppose the thumb shows the direction of current and the finger curls shows you the direction of magnetic field. Okay, so suppose the thumb, this is the conductor, then thumb is in the direction of current, and when you curl the finger, so that will give you the direction of magnetic field. So that is the direction of magnetic field. Curling the fingers will give you the direction of magnetic field, and this is the thumb in which the current should flow. So direction of the current should be in the direction of thumb, then the finger curl would give you the direction of magnetic field. Now coming to the application of the Biot-Savart's law, you can calculate the magnetic field surrounding a thin straight conductor. So suppose there is a straight current carrying conductor like this. It has the current I in the forward direction, in the upward direction you can say. And suppose we want to calculate the magnetic field at any point P, and because this is a finite length conductor, so from the bottom end and the upper end we will line join, and we will measure this angle. Let us say this angle is phi 2 and this angle is phi 1. Okay, this is the A and this is the B. So this is the direction of current in the upward direction, and the perpendicular distance from the conductor to point of interest is say A. So the magnetic field at point P, because of this current carrying conductor which is having the direction in the upward, so B is equal to mu naught into I upon 4 pi A sine phi 1 plus sine phi 2. And because this P is in this direction, so when you curl the finger, it will go inside. So here the magnetic field will be inwards. Okay, magnetic field will be inwards. So that is the direction of magnetic field. Because of any finite length current carrying conductor, if they ask you to calculate the magnetic field, just line join from the upper end and the bottom end, and then calculate the angle. From the upper end, the angle measured is known as phi 1, and from bottom, the angle measured is known as phi 2. There are golden points. We can say the important point that the direction of magnetic field vector is always perpendicular to the plane of I and dr, and magnetic field on axis is current carrying conductor. Okay, along the axis means magnetic field always exists in the perpendicular direction. It will not exist in the direction where the conductor is placed. So in this direction AB, the magnetic field will be 0. The tangent draw at any point on the field line represent the direction of the field at that point. Suppose we have drawn this, so I want to calculate the magnetic field direction in this. So the direction, the tangent that draws in this particular point will give me the direction of magnetic field. So whenever you draw the tangent at any point, that will give you the direction of magnetic field. Field lines will never intersect, and at any place crowded field lines gives you the stronger field, while the distinct field lines represent the weaker field. And if the field lines are equidistant and straight, then the field lines are called uniform, otherwise not uniform. When the current is straight, the field is circular, and when the current is circular, then the field is straight, just opposite. And when the wire is in the place or plane of paper, then the field is always perpendicular to the plane of paper. Okay, now for example, if you will see, there can be some cases like case number 1. If you will take this case number 1, then suppose this is the current carrying conductor, and it is of infinite length, so minus infinity to infinity, and we want to calculate the magnetic field at point P. So because it is infinity, when you will join this, this will be the angle 90 degree. Okay, so this phi 2 will become 90 degree. This phi 2, phi 1 is also 90, phi 2 is also 90. So in this case, the magnetic field will be mu naught into I upon 4 pi A. And when you put this value sine 90 plus sine 90, it will be 2. So the magnetic field will be this mu naught I upon 2 pi D or 2 pi A. That perpendicular distance is A. So whenever there is a infinite line, current carrying conductor is having the length infinite, then at any particular point, if you want to calculate the magnetic field, it is mu naught I upon 2 pi. Now suppose case number 2, if we have the length like this, it is finite, it is suppose somewhere at origin, and this is at infinity, and you want to calculate at this point. Okay, now let us calculate somewhere here at this point P. Then this angle would be 90. This angle is phi 1 equal to 90. And then the phi 2 is equal to 0. Phi 2 is 90, phi 1 is 0. B equal to, when you take phi 1 equal to 0, sine 0 is 0, phi 2 is equal to 90. So this is mu naught into I upon 4 pi into A. That is the perpendicular distance. This is phi 1, upper angle is always phi 1. So when it is infinity, so upper angle will make 90 degree. So this is upper one will be having 90. when it is at infinity. Okay, when it is at infinity, then the electric field will be mu naught I upon 4 pi A. Okay, suppose there are two conductors placed like this. This is first conductor carrying a current in this direction. There is a second conductor having a current in this direction, and they are separated by a distance of 5. Okay, so they are having the distance of 5. This is 5 ampere current flowing in the upward direction, and this 2.5 ampere current in this direction. The distance is 2.5 from this point. At point P, what is the magnetic field? Okay, so our options are mu naught upon 2 pi inward, or mu naught upon 2 pi outward, and 5 mu naught upon 6 pi inward, and 5 mu naught upon 6 pi in outward. What will be the magnetic field at point P? If there are two current carrying conductors, they are infinite, both are infinite long. Okay, they both are infinite long. Then at point P, what will be the magnetic field? Since it is a magnetic field follows the superposition law, so for individual current, for individual, we can take the magnetic field and then we can add it. So the formula is mu naught into I1 divided by 2 pi A, and the direction would be, because the current is flowing in the upward direction, the thumb is in the direction of current, then the finger, when you curl, it will be inside. So cross, and hence mu naught into I2 divided by 2 pi A. For this perpendicular distance is suppose A1, this has the perpendicular distance A2. For this also, that is inside. So both will be going to add. So mu naught upon 2 pi is common. The current from the in the first conductor is 5 and the distance is 7.5. The current in the upward direction is 2.5 and the distance is also 2.5. So it is mu naught upon 2 pi is 2 by 3 plus 1, and it is completely inward. And when you will solve it, 5 mu naught upon 6 pi inward would be our answer. Option C would be our answer. Okay, so this type of questions can be asked. Now suppose there is one more example we can take. Okay, this is first example. This is first example. This is second example. This example can be like this. Suppose we have a y-axis and this is having the x-axis. Okay, suppose this distance is d. This is I. This is y-axis we are taking. And suppose this current is flowing in this direction, I. This is x-axis, obviously. Now, what is the magnetic field at origin? Magnetic field at origin. We want to calculate magnetic field at origin. Magnetic field at origin, this point O. Let me give you some options. Mu naught I upon 2 pi d, and this is also outward. Mu naught I upon 2 pi d, it is inward. Mu naught I upon 4 pi d outward, and mu naught I upon 4 pi d inverse. What would be the answer? See, as I told you that the magnetic field will not exist in the direction of the axis. So because there is a conductor which is coming from the infinite, but it is in the direction of the point of interest is in the direction of the or in the axis of the conductor, then the magnetic field will not exist because of this part of conductor. Similarly, because of this part of conductor, the magnetic field will not exist because it is lying on the axis of the conductor. So the point is lying on the axis of conductor. But here, when you will consider this part, say first part, and this is say second part. So this is from 0 to minus infinity, because this is 0 and this is minus infinity, this is infinity. So it is going up to 0 to minus infinity. It is going from 0 to plus infinity. So when we make both of them together, okay, when we take the both of them together, then because of this the current is flowing in the downward. So if the thumb will show in the downward direction, it is a semi-infinite condition. So in case of semi-infinite, we have seen that in case of semi-infinite, we have seen that the magnetic field is mu naught upon 4 pi perpendicular distance, and the direction thumb is showing in the direction of flow of current. Then the when you curl the finger, it will be outside, and plus mu naught into I upon 4 pi d, and from this side also it is outward. So they both going to add, and mu naught upon 2 pi d into I outward you will get. That is option number A. Option number A you will get. Okay. Now you can also consider the equilateral triangle, or the square, or the regular hexagon. For all of them, you can calculate the magnetic field. For a regular polygon, that is important that you can use then this formula for any type of regular polygon. So magnetic field at the center of magnetic field at the center of a regular polygon of n sides. Okay, so the for answer for this is the magnetic field, if you want to calculate, that is n times mu naught into I divided by pi a, then sine pi by n and tan pi by n for any regular polygon. Now we will apply this. N is the number of side. Okay, n is what? Number of side, n sides. So now let us apply this particular formula for calculating that for the two different or the three different conditions, like rectangular, sorry, triangle, square, and let us say hexagon. Okay, suppose the current is flowing in this direction. The side is A. The current is flowing in this direction. The side is A. This is a square. This is a triangle, and this center we want to calculate. The side is A. So if I apply the formula, then how many sides we have? Three. So 3 mu naught I upon pi A. Then sine pi by 3. And then 10 pi by 3. So how much it is? 3 mu naught I upon pi A. Sine pi by 3 is root 3 upon 2, and 10 pi by 3 is root 3. So root 3 and 3, we will get 9 mu naught I upon 2 pi A. Okay. Now in this case, B is equal to 3 mu naught. Oh, sorry, this is 4 mu naught now. Okay, because the number of side is 4. So 4 mu naught I upon pi A. Then sine pi by 4 and 10 pi by 4. So 10 pi by 4 is 1 and sine pi by 4 is 1 by root 2. So 4 mu naught I upon root 2 into pi A. So if we can root 2, if we multiply, then we will get 2 root 2 mu naught I upon pi A. Similarly, here if I calculate this, B is equal to 6 side, we have 6 mu naught into I upon pi A, and sine pi by 6, that is 1 by 2, and 10 pi by 6, that is 1 by root 3. So it is root 3 into mu naught I upon pi A. So this would be our magnetic field. Okay, so these are the three important conclusion for the magnetic field for a regular polygon. So important it is, because direct formula, if you remember, then you can easily solve the questions within the time period. Otherwise, you have to derive it. So these are the some standard formulas that you have to remember. Now we will take the magnetic field. Okay, the magnetic field at the center. Magnetic field at the center of current carrying circular loop, you can say, or you can say the coil. So what will be the value here? The circular loop, when it has the number of turn equal to 1, then at the center, B is equal to mu naught into I upon 2 into R. Okay, that is the circular loop. I am talking about the circular loop. Okay, so this type of loop we have. There is a radius R and the current is I. The current, direction of current, you can take opposite, because it should be looking like outside. No? The When I is the direction of current in the circular coil, so I is the curling of the finger is in the direction of current. So when you curl the finger, the direction of current should show the direction of current will show the curl of your finger, then thumb will point in the direction of magnetic field. So here, if you curl your right hand finger in the direction of current, then thumb is outside the screen. So here the magnetic field is outside. And when the number of turn is more, then you just multiply by the number of turns. Then you can also calculate the magnetic field B at the center due to the circular arc. So B is at the center, we are saying B equal to mu naught I into alpha, that is the angle, upon 4 pi r. Okay, so circular arc means you can say like this, and this is the circular arc. We have a angle alpha. We have a angle alpha. The radius is r. The current it has is suppose I. This is the current. Okay, and there is no need of length, so mu I r alpha, right? So this is the formula. So you can also write in terms of for a circular arc, complete value is b. So that is, suppose that value is b naught. So suppose this is mu naught I upon 2 or mu naught I upon 2r. So you can say mu naught I upon 2 pi, b naught upon 2 pi into alpha. In terms of the complete loop, if you know the electric magnetic field at the center due to the complete loop, then for a particular section, if you want to calculate, just multiply it by alpha by 2 pi. So when you multiply by alpha by 2 pi, you will get the for a small section of the circular loop magnetic field at the center. Is it clear? Now magnetic field at the axial point of the current carrying coil also we can write. So magnetic field B at axial point, at axial point of the current carrying circular coil. Okay, so at the center, if suppose you want to calculate, the general formula is, let me draw the diagram also. This is suppose the circular loop. This is the axial line. There will be a question from this topic, okay? Very important topic. R, theta, and suppose this distance is x. The radius of the circular coil is r, and this is the point where we want to calculate. So in this case, the bx, okay, in the this direction, bx, magnetic field in this direction, this is bx. What will be the bx? So that is mu naught into I into r divided by 2 x square plus r square to the power 3 by 2. That is your r square and x square. Yes, mu naught I into r square, mu naught I into r square upon 2, and x square plus r square to the power 3 by 2. So what will be the value at center? At center means the x is 0. At center, x is 0. So at center, the x is 0. So in this case, the b naught, that is center, I am saying as b naught. So x will be 0. This point p will come here. So this x is 0. So this will be mu naught I upon 2r. Mu naught I upon 2r. Okay, so that is how you calculate the V at the axial point. Magnetic field at the center of any geometrically symmetrically circuit loop, है ना? Geometrically symmetrical loop at the center will be zero. Like for a square, for a circle, okay, this at the center the magnetic field will be zero. Cube, triangle, all these are having the geometrically symmetrical, so that's at the center it would be zero. Suppose I give you one question and it is asking related to the topic that we just discussed. Suppose this is the circle, okay, and actually this is the main part of the conductor. The red line is the main part of the conductor. Okay, that is the conductor. Okay, now let us say this is the actual conductor at which the current is flowing, which is having the radius A. This is having the radius A, and this part is having the radius B. No, don't take it because there is some part which I have missed. The data I don't have exactly. Now we have a Ampere's law. Okay, what is that Ampere's law? The Ampere's law says that the integration over the closed loop B dot dl. Okay, the integration over the closed loop B dot dl is equal to the current enclosed multiplied with mu naught. Okay, that is we will say that there is suppose a closed loop like this, and we have a current say I1, and say this is I2, and say this is I3, and this is the closed loop. Okay, and there are some current like here also there are some current as dot I5 and I4. Then according to this law, we will write that the current enclosed, that is summation of B dot dl, would be equal to mu naught into, if I suppose take the dot as positive, dot is positive, so this is I1 plus I3 minus I2, because this is only the loop. Inside the loop, these are the currents that are enclosed. So we will take I1 minus I2 plus I3. So this is independent of the size and the shape of the closed loop. Okay, the law is independent of the size and the shape of the closed loop. Any current outside the closed path will not be included, and the inside will be taken as negative and outside is taken as positive. So this is the Ampere's circuital law, or simply Ampere's law you can say. Like in the electrostats also, we have seen that there are a solid conductor conducting sphere and there is a hollow conducting sphere, then non-conducting and conducting sphere, and we have calculated the electric field at the various points. Similarly, we have very important relation in the magnetic field also due to the infinite long solid cylindrical conductor. So suppose we have a infinite long solid conductor, so we will calculate the B, magnetic field B, due to infinite long solid conductor. Okay, so there is a solid conductor. So we are taking like this, and here you can see that there is a flow of current in this way in the upward direction. So that is the current I in the upward direction, and we want to calculate the magnetic field because of this line, this current conductor. This whole conductor is having the current. No? This is not only through the center. This we are saying that it is having a current in the complete conductor. The current is through this complete conductor like this. Now, because we want to calculate the magnetic field, suppose we want to calculate the magnetic field inside. So first case, when the point of interest is less than the radius of the cylinder. The radius of the cylinder is suppose capital R. So we want to calculate inside, then this B inside mu naught into IR upon 2 pi R square. And exactly on the surface, it will be at the just on the surface BS. This R is equal to capital R, so this is mu naught I upon 2 pi R. And in the third case, when we want to calculate the outside, it will be like a same as the single conductor, so which is mu naught I upon 2 pi R. These are the formulas. So you have to remember this formula, because the graph, they will ask you about the graph in this case. So we have seen like same, it is same like a non-conducting sphere. In the case of electric field, it is having the straight line because there is a direct relation between R and B, and then it has the maximum value, and then it will starts decreasing. Sorry, this is B, this is R. This is the maximum value BS. Okay. Now, next we will discuss about these are the some standard points. So now let's write about the B due to the solenoid and the toroid. That is also important, and the question has been asked from this B due to solenoid. So whenever they ask you about the B at the solenoid, so B due to solenoid is first of all you have to understand that what is solenoid. It is nothing but a coil which has certain length and used to produce uniform magnetic field of long range. It consists of conducting wire which is tightly wound over a cylindrical frame. Okay, so like a simple inductor, you can say, suppose you have an iron core like this, then if you wound the wire in this, if you wound the wire like this, then it will form a inductor like structure, and that is known as solenoid. So in this case, the solenoid, if you have a finite length solenoid or infinite length solenoid, you can calculate it, the magnetic field. So it is at the axial point. Suppose at any point P inside you are calculating, Let me write in this form mu naught into Ni. Hmm. So B into length of this conductor, the solenoid is L. So B into L is equal to mu naught into number of turns into current flowing through this conductor. So B is equal to mu naught into N divided by L into I. Okay, that is the B. Due to the solenoid, if you want to calculate, then the magnetic field is B is equal to mu naught, and I is the current flowing through this current carrying conductor which is wounded on the core. And if suppose this is the iron core, then you have to take this mu r also. That mu r also be multiplied here if you are taking in the iron core. Okay. Magnetic field inside the core of a toroid. Toroid is nothing but the circular structure. Suppose we have this type of circular iron core, and suppose we wound the, actually this is circular structure. Okay, now suppose we wound the wire here like this. In this core I have wound the wire. Okay. The current is entering from here I, and this is leaving from this side. It has some mean radius r. So this B is equal to mu naught into N into I, where N is N upon 2 pi Rm. Rm is mean density, mean radius. Rm is mean radius. N is number of turn. Mean radius means the inner radius and the outer radius R1 plus R2 divided by 2. So that is the mean radius. That is the formula mu and I. I will show you the question from this particular topic also. Don't worry. Now we have a Lorentz force equation. So like a magnetic force, if you want to calculate magnetic force on moving charge. Okay, magnetic force on moving charge is Fm is equal to Q into V cross B. That is the magnetic force due to the magnetic field, that means magnetic force on a moving charge. If the charge is moving in the presence of magnetic field, then the force exerted by that charge is Q into V cross B. Now this is also important that motion of a charge particle, motion of a, hello Sanket, good evening. Motion of a charge particle in uniform transverse magnetic field. Yes, Ankit. So if you have any query related to your preparation of for the Airport Authority of India, you can just comment in the comment section. So QVB, because the charge is in the presence of magnetic field, so that is QVB, and because it is in the circular motion, it will form a circular motion. So we will have the mv square by r, that is the centripetal force. Okay, like here we have a magnetic field like this. Suppose in this region we have a magnetic field in the perpendicular direction of a motion of a charged particle. These are the magnetic field. This cross is showing the magnetic field. Now here you have a circular motion because of the magnetic field and the charge is moving. So because the charge is moving in the circular direction, so that is this centripetal force we will be applying to compensate this magnetic force. So both will be equal. then you can calculate the radius of the circular path, that how much when it is moving in the circular path, then what will be the radius formed by this. V will be in this direction. Definitely V is in this direction. The cross is showing the direction of magnetic field. This cross is showing the direction of magnetic field. The charge is somewhere here and the mass of the charge is m. Okay, so anything that you have in your mind that you want to ask? Here you all can also draw the magnetic force on the current element. Suppose there is a current element, so magnetic force on current element. This was the magnetic force on the charged particle. We have calculated the magnetic force on the current element. So suppose there are two magnetic conductors placed. So because of one magnetic conductor, the magnetic field will be generated, and because of that magnetic field, the other conductor will exert a force, and that is given by I into dl cross b. That is the force exerted on the small length dl. Okay, suppose we have a magnetic field like this. This is the external magnetic field. This magnetic field is external, and here we have a one conductor which is having the length current element ideal. So the angle between them is theta. So in this case we will call it as dfm, which is inside. Okay, you should also know that there are two conductors, infinite conductors placed parallel, and if the current is flowing in the same direction, and if the current is flowing in the opposite direction, then what happens? If there are two infinite conductors, they are placed parallel to each other. When they have the current in the same direction, then they attract each other. Okay, they attract each other. There is some distance d, so there is a attractive force between them. And when the current direction is opposite, so there will be a repulsive force. The distance is same d. So what are the value? Mu naught I1 I2, how much it is? Yes, mu naught I1 I2 upon 2 pi d. If the length is finite, then you can multiply with the length also. Next is ray optics. Before going into the ray optics, there is one more thing which is left, is the magnetic dipole. So magnetic dipole, torque on the magnetic dipole. Suppose there is a magnet like this. It is rotating about this particular point. So if it is rotating about this particular point, then in the clockwise direction, suppose it is rotating. Okay, here it is rotating. So they will create a magnetic dipole moment. And that magnetic dipole moment for a bar magnet that we have seen is equal to tau equal to force into perpendicular distance between the force couple. So there is a force here, the force here, and there is a force in this direction. So what is the value of tau? That is nothing but m into b and L sine theta. Okay, the magnetic field is uniform. the magnetic field is in this direction, and this is the magnetic field direction, the magnetic field direction, the magnetic field direction. So the dipole moment is tau is equal to mb into L sine theta. So let's solve some questions related to. Before going into the ray optics, I would like to show you the some previous year questions related to the electric circuits and also from the magnetostatic. So there is one question, that is the three resistors R1, R2 and R3 have their resistance values in the ratio of 2, 3 and 4. They are combined in parallel, then their equivalent resistance is 24, then their individual resistance R1, R2 will be. What should be the value? There are four options. These are the four options. So options A, option B, option C and option D. Okay. So let R1 is equal to 2x, R2 because they are in the ratio of 2, 3, 4. So we can write 2x, 3x and 4x. All these are connected in parallel. So the equivalent resistance R equivalent is 1 upon 2x plus 1 upon 3x plus 1 upon 4x. So if we solve this, this is nothing but the 12x is LCM. This is your 6x, 4x and 3x, 2x. Sorry, wait. 6 plus 4 plus 3 only. So R equivalent will be this R equivalent is also given. Na? So this R equivalent is 12x upon 13. So here if I calculate the x, it is 13 into R equivalent, which is 24 divided by 12. So it is 26. It is given as 26 ohm. So because all are in the ratio of 1, 2, 1, 3 and 2, 3 and 4. So if the x is 24, 26, then R1 is 52 ohm, R2 is 78 ohm and R3 will be 104. That means our correct answer will be option A. Okay, so that is the previous year question. Previous year questions. We are solving the previous year questions. Next, a copper wire of uniform cross section is 3.4 into 10 raised to power minus 5 meter square, carries a current of 4 ampere. The magnitude of electric field. What will be the magnitude of electric field? These are the four options. So we know that the electric field is volt divided by distance or length, whatever you want to write, L or D. And V is also equal to IR, so IR upon L. So now electric field is I into rho into L upon A, right? So rho into L upon A, and already there is a L. So this L and L will get cancelled. So electric field is I into rho upon A. So how much is the rho? Rho is the 1.7 into 10 raised to power minus 8, and I is 4, and the area is 3.4 into 10 to the power minus 5. So it is 2 into 10 raised to power minus 3. So right answer will be option B. Volt per meter. Clear? So these are all our previous year questions. Now let's solve the next question. The magnetic field in a plane, the magnetic field in a plane, electromagnetic wave is given. Okay, remember that this is nothing but a electromagnetic wave. So the magnetic field in a plane electromagnetic wave is given by By is equal to 0.2 micro Tesla sine 8 pi into 10 raised to power 2 Z plus 6 pi into 10 raised to power 11. Then the electric field is. So it is given in the home micro. Yes. So see, if we want to calculate the electric field, because this is y component of electric field, and this is traveling in the z direction. Here you can see that the direction of propagation is in the z direction, and the electric magnetic field is in the y direction. The direction of magnetic field is y. So definitely the electric field will be in the x direction. So these are the four options. So these two options you can definitely eliminate because the magnetic field cannot exist in the same direction as the magnetic field. So there are two options will be eliminated. Now this in the term inside will remain same. There is no change in that. Only we need to check these two things. So we should know that what is the relation between this B and H. So B is equal to E upon, this is suppose, let me write once. We know that related to the impedance, this is eta is equal to E by H. Okay, and we want to write H. So H is equal to E upon eta. We want to write E. So we want to write E. So if we want to write E, so E is equal to eta into H. Eta is 120 pi and H is B is equal to mu H. B equal to mu H. So H is equal to B by mu. Cool gamer, I can teach in Hindi also, but I think this channel is mainly going to provide this in English only. So we are not going to cover it in Hindi. So 120 pi into mu naught is 4 pi into 10 raised to power minus 7, and this B is 0.2 into 10 raised to power minus 6. So this pi and pi will get cancel. ठीक है, कूल गेमर, अगर आपको कुछ डाउट है तो आप पूछ सकते हो, देन यू कैन डेफिनेटली आस्क. अगर आपको कोई डाउट है तो यू कैन आस्क हियर. सो वी विल गेट द 6 into 10 to the power minus 6 and divide में आपके पास 10 to power minus 7 है. So you will get 60. So 60 means option B will be the right answer. ठीक है, ऑप्शन बी जो होगा वो राइट आंसर होगा. इस पूरे को आपको सॉल्व ही करना है ना. आप कैसे सॉल्व करोगे दैट इज अप टू यू. आपको बस कैलकुलेशन करना है. मैं एक बार लिख देता हूँ वापस से. सी व्हाट आई हैव रिटन हियर इज ईटा जो होता है फ्री स्पेस के लिए, अगर आपको कुछ नहीं दिया है तो आप फ्री स्पेस ले लोगे. बी इज इक्वल टू म्यू एच होता है. म्यू की वैल्यू म्यू नॉट मतलब ये वाला जो म्यू नॉट है, ये म्यू नॉट है. म्यू नॉट की वैल्यू 4 पाई इंटू 10 पावर माइनस 7 इंटू एच. एच की वैल्यू यहाँ से हमारे पास आ जाएगी. सॉरी वेट, यहाँ पे म्यू नॉट आएगा. ये म्यू नॉट है. तो बी की वैल्यू हम लोग लिखे 0.2 और ये माइक्रो में दिया था तो सो 10 टू पावर माइनस 6 एंड दिस म्यू नॉट इज 4 पाई इंटू 10 टू पावर माइनस 7. इस पूरे को सॉल्व करके देख लेना. यू विल गेट 60. सो यू विल गेट 60. दैट मींस ऑप्शन बी वुड बी द राइट आंसर. Okay, can you solve this question? A parallel plate capacitor with the plate area A and the plate separation D with the vacuum between the plate has a capacitance C naught. The space between the plate is filled with the two slabs of the same area, but their thickness is D by 4 and the 3D by 4. So two slabs, but दोनों का जो material है, yes, they have filled with the dielectric. So what will be the capacitor? So the situation I will tell you, there are four options given to you. Can anybody answer this question? This situation I have drawn here. This is the first case जब यहाँ पे आपके पास air filled है, ठीक है, air filled है, and the distance between the plate is d. The plate area is A. Okay. So this is the plate number 1 and this is the plate number 2. Now this is also the plate number 1, this is plate number 2. But now we are saying that this d by 4 distance is covered with the dielectric, let us say epsilon r1 equal to 2, and this is covered with the epsilon r equal to 4, and the remaining distance is 3d by 4. Okay. So in this case, the what is the capacitance? C naught is equal to epsilon naught A by D because it is air. Now in this case, because this is the series connection of the two capacitance, the series connection. So in the series connection, we have C equivalent is equal to C1 C2 upon C1 plus C2. It is the capacitance it is asking for with respect to the air. So C1 कितना हो जाएगा? Epsilon naught dielectric is 2 and area will remain same. The distance is d by 4. This is a C1. C1 is epsilon naught into epsilon R1 A by D. So distance यहाँ पे d by 4 है. Epsilon R1 की value substitute करें. So now this is epsilon naught. Epsilon R is 4 into area A divided by D. D is 3D by 4. So whole divided by, you will have to add it into 4 divided by 3D. Let me write in this form. Now, if you take the, how much we can take common this epsilon naught A d by 4, epsilon naught A d by 4, epsilon naught A d by 4 is going to be cancelled, and we will left with epsilon naught A upon D. This 4 will go here. So 16 into 2, 32 by 3 in the numerator we are getting. And in the denominator we are having the 2 plus 4 by 3. So it is epsilon naught A by D, which is C naught. 3 and 3 will get cancelled, and this is 10. 32 upon 10 means 16 by 5. So 16 by 5. Okay, 32 by 10 is 16 by 5, and epsilon naught A upon D is C naught. So we can write 16 by 5 C naught. So option B will be the right answer. Got it? Now you solve this question. There are again four options given to you: A, B, C, and D. These are the four options. A square sheet of side 5 centimeter is placed in an electric field such that the normal unit vector of the sheet is root over 3 by 2 plus 1 by 2j, then the electric flux is. So what is the electric flux? When you calculate the electric flux, this is I is equal to integration over the surface, the electric field E dot ds. Okay, so here if I calculate it, integration over the vector E magnitude and its direction. So that magnitude and the direction is given. The magnitude is 1.6 and the direction is I cap. Dot product with the ds magnitude and the direction is an, which is normal direction. So the electric field is 1.6 into 10 to the power 4. It is having the constant and integration over the surface. This is I cap dot. This ds is, let me write in this form. Let me write in this way so that you will get understand. E is 1.6 into 10 raised to power 4 into I cap dot product with the ds, and the normal vector is given as root 3 by 2 I cap plus 1 by 2 j cap, and we have to integrate all this. So first of all, before integration, we will take the dot product, and when you take the dot product, you will get 1.6 into 10 raised to power 4 into root 3 by 2. I and I will have dot product as 1 and I dot j will be 0, and integration over the surface ये कितना हो जाएगा ds. So यहाँ पे आ गया 1.6 into 10 to the power 4 root 3 by 2 into area of the square. Area of a square. So what is the area of a square? This is 0.8 into 10 raised to power 4 into root 3 into 25 centimeter. So 10 raised to power minus 4. So it is 4. This is 0.2 into root 3 into, this will get cancelled. So we can cancel it. It's better. So we will have root 3 into 25 into 8, 200. So that is 20. So 1.73 into 20. So it is 34.6 only. 34.6 Newton meter square per coulomb. So that will be our answer. Yes, Aman. Very good. तो अमीन आप कैलकुलेट कर लिए, खुद से सॉल्व किए हो अमन? सो प्रिपरेशन है ना? ये तो बेसिक इलेक्ट्रिक है, इलेक्ट्रोस्टैट्स है, तो आपकी प्रिपरेशन है. देखो इलेक्ट्रोस्टैटिक यानी 12th वाले फिजिक्स का पार्ट ज्यादा इंपॉर्टेंट रहता है. आप एयरपोर्ट अथॉरिटी ऑफ इंडिया का प्रिपरेशन कर रहे हो, सो इफ यू आर प्रिपेयरिंग फॉर एयरपोर्ट अथॉरिटी ऑफ इंडिया देन you are good. Now try to answer this one. So two batteries E1 EMF 3 volt, internal resistance 0.5, and E2 6 volt and resistance 1 ohm are connected in series. So this is E1, which is 3 having the resistance, and this has the 6 volt having the resistance 1, are connected in series by the positive terminal of E2. The positive terminal of E2 to the negative. Yes. A third battery E3 is connected in the positive terminal to the positive terminal of E1. Okay. So in this way it is connected. Then the equivalent EMF will be. What is the equivalent EMF? This is E3. This is E2. E3 is 6 volt again, and this is also 1 ohm. C you are saying? The equivalent. Okay, so we can take the nodal here and we can take the ground over here. So because we want to apply, so V minus 3 minus 6 upon 1.5, which is 3 by 2, and we can take V minus 6 by 1 equal to 0. So it is V upon 1.5 minus 9 upon 1.5 plus V minus 6 equal to 0. So it is nothing but a 3 by 2. So 2 3 by 2. So 2v by 3 plus v equal to 6 plus 9 upon this is 3 by 2. So how much it is? 5v upon 3, and it is 6 plus 6. So it is coming as 12. So it is 5v is equal to 36. So it is coming as 7.2. 7.2, yes, 7.2 is the right answer. Okay, now can you answer this? Again, there are four options: A, B, C, and D. Consider an ideal toroid of average radius 16 centimeter with the 240 turns. A current of 10 ampere is maintained in it. The magnitude of magnetic field inside the toroid. The magnitude of magnetic field inside the toroid. What would be the answer of this question, Aman? So we discussed that the magnetic field this B inside the toroid is given by mu naught into Ni. Okay, and where mu naught is the mean radius. C are only getting, okay. So this is number of turns divided by 2 pi into mean radius into I. This is the formula. So 4 pi into 10 to the power minus 7. How many turns? 240 turns divided by 2 pi. What is the mean radius? So mean radius is Rm is equal to R1 plus R2 divided by 2. So it is having the average radius. Okay, sorry, already given 16 centimeter. So it is 16 into 10 raised to power minus 2 into I current is how much? 10 ampere. 10 ampere it is given. So 2 pi and this will get cancelled. You will get 2, and we have 2 into 2 4 24 divided by 16. This part I am taking separately, and 10 raised to power minus 6. This 10 I have taken, and this plus 2. So we will get 3. 3 into 10 to the power minus 4. And one more 10 we are left with, na? This 10. Yes, so 3 millitesla. What you said, C, na? Yes, 3 millitesla. Good. 3 millitesla. This 10 is also there. Na? So 1, 2, and this 4. 7 minus 4 is 3. So we will take this as 5. Minus 5, and then from denominator it is coming as plus 2. So minus 3. 3 millitesla. Option C. Yes, Aman. Good. Now answer this. Yes, yes, 10 to the power minus 3. I have corrected that. That 110 I have missed actually because that I have written in this formula, so it was not clear. So 2 charges A 48 picocoulomb and 36 picocoulomb are located at 3 centimeter and 4 centimeter. The magnitude of electric field at 3, comma 4. 3 centimeter and 4 centimeter. So we have a charge of 48 picocoulomb and 36 picocoulomb. What is the answer you are getting? So electric field due to the 2 point charges. So we will apply simple magnitude only because there is no need of direction. So E is equal to, we want to calculate at the 3 comma 4. So it is 3 comma 4, suppose somewhere here. So for here the distance will be 4, and for this the distance would be 1. This distance is 1. Okay, and this distance is 4. Option C. So this distance is root 17. So KQ by R square. So KQ1 by R1 square plus KQ2 by R2 square. Just correct me if I am doing anything wrong, Aman. So Q1 is 48 picocoulomb. So 48 into 10 to the power minus 12. The distance is 4. That is 16 plus KQ2. Q2 is 36 into 10 to the power minus 12 divided by what is the distance between the 2 point charges which is placed at 4 and this 3 comma 4. So root 17 only, na? So that is 17. Okay, so it is 3. So we will get 9 into 10 raised to power 9 into 10 raised to power minus 12 is equal to 3 plus, we can, 36 is at 0 comma 4, no? 36 is at 0 comma 4. Yes, 36 at 0 comma 4 and 48 is 3 comma 0. Okay, 0 comma 4 is there. Sorry, the distance I have taken. Yes, because the value that I saw, I felt like it is somewhat absurd. Yes, because the root 17 is not going to give us any value. So that's why I was thinking, and that's why I asked if I'm doing anything wrong, then just let me know. Yeah, then it is very, very easy because 48 picocoulomb is at 3 comma 0 and 0 comma 4 means somewhere here. 0 comma 4. right? So kq by r square, that is fine. And here it is, the distance is 3, so this is 9. So this is 3 and this will be 4. Why we are not getting the right value? Okay, we want to calculate 3 comma 4. 48 is at 3 comma 0, so that the perpendicular distance will be 16, and here the horizontal distance would be 3, so 9. So 4 here and 3 here, 7. This is origin. So this is the point where we want to calculate. Yes, Soman, tell me. Resultant we need to calculate now. So the electric field is in this direction, the electric field is in this direction, so the resultant electric field will be in this direction. Okay, so this E1 is in this direction, then E2 is in this direction. We have to find the direction, so we need to write the root over it. Okay, we have to find the root over it. So that is this is in the upward direction, so this first term is in the J direction and this term is in the X direction, so you will write I cap. Yes. So 9 into 10 raised to power minus 3, and this is 3j plus 4i, and this is your electric field vector. We need to write in the terms of vector here, because otherwise you are going to get the wrong answer. There is nothing in the option, but that's why it will become easy to find your mistake. But the options should be in the minus 3, right? But the point is also in the centimeter. That is another catch here. The point is also in the centimeter, so there is another catch, that you should be having 10 raised to power minus 4. So into 1 upon 10 raised to power minus 4 should also be there. So it is 90 into root over 3 square plus 4 square. So you are going to get 450. Okay, you are going to get 450. Hence, you will say the right answer is. So there is another catch. So these are the common mistakes that anyone can do. Okay, so that is the first mistake that we can forget. We can not write. If suppose somebody doesn't write in the form of direction, then he will face the problem like I did. Okay, that is another thing. I thought that it is a easy question, so let's take it as a simple in the magnitude form. So that's why I found mistake. The second mistake that one can do is it is in the centimeter, so the distance you have to keep carefully. That is 10 to the power minus 4, right? Okay, guys. So this was all previous year questions. So we will solve more questions somewhere whenever we get time here, because now we have only 4 days to solve the problem. So we are now leaving this here at this point. So thank you, Aman, for joining and answering the questions. Okay. So all the very best for the examination. Now tomorrow is Sunday, and then day after tomorrow, maybe 25th. After that, you have 2 days left. So revise thoroughly. That I have already given you an idea that which kind of questions can be asked and what are the topics that you have to cover if you want to solve the more questions from the physics. Thank you, Aman. Thank you. And this is our contact information. So if you have any doubt and anything, if you want to ask regarding upcoming batches, then you can just call in this number. And this is our website. Okay, and the email ID. Thank you. And don't forget to subscribe this. channel, and also join our other social media platform where you can connect and get information that what is going to be conducted for all of you for free, and also some special classes for. Thank you, Srinidhi. Okay, so you are also there, so that's good. Thank you.